Okay, in section 3.2, we talk about differentiability. So we talk about when functions are differentiable, so when can you take the derivative, and when can't you. Big definition here, differentiable. It's when the derivative of a function f of x can be taken or exists at a particular x value. So for something to be differentiable, it just means we can take the derivative. There are some scenarios, though, where we cannot take the derivative. So functions are going to have undefined derivatives when the slopes of tangent lines differ drastically from one side of a particular x value to the other. Thus, the slope cannot be calculated at that given point. Remember, all this is going to tie to, so when we see the word derivatives, we are thinking slope. So most of these scenarios where we're not going to have a derivative, it's going to be where we have issues with the slope. So that first one, drastic change from left to right. Second bullet point, we have a function that does not exist. So if the function doesn't exist or it's not continuous at a given x value, you can't take the derivative there. So looking at examples here of such points where a function would not be differentiable, we have what's called corners. With a corner, it's going to be a drastic change in slope. So when I look at this right here, at x equals 2, we have a drastic change in slope. We are going from a slope of positive 1 to a slope of negative 1. Since that slope is drastically different, we can't differentiate it. So we got a corner there. And then we also have a corner over here in this weird looking function. So I'm going from a negative to a positive slope, and it's a sharp change. It's not a gradual or anything. So at x equals 1, for this diagram, this graph right here, x would not be differentiable. We also have a scenario where we have a cusp. These are extremely rare. Instead of having like a straight line in, straight line out or something, you have kind of like almost like square root functions, I'll call them, where they're meeting and then they kind of have a point, almost like a bird, almost kind of looks like. But those are known as cusps. Those are extremely rare. Number 3 would be more common. For number 3, we have vertical tangent lines. So if I were to take the derivative and we were to end up with a vertical tangent line, that is also not differentiable. So looking at the cube root of x, if I were to draw the tangent line right at x equals 0, my derivative, or my tangent line, would be vertical. Vertical has a slope of undefined, hence the derivative would be undefined. Same deal with the circle. We got the tangent on the left, tangent on the right. Both of those, if we were to find the derivative, we would get a line, or a tangent line that has a vertical, that is vertical, so the slope would be undefined. Last scenario would be a discontinuity. If the function is not continuous, you can't differentiate. So looking at this, your justification for it not being differentiable, we would say something like it is not differentiable at x equals negative 2 because f of x is not continuous at x equals 2. So at any point, if the function is not continuous, we are not going to be able to differentiate it there. So here I got x equals negative 2. And then on this one, it would be x equals negative 1. All right, so we looked at those 4 scenarios where the function would not be differentiable. It's going to lead us into our differentiability theorem. The differentiability theorem says is that if f has a derivative at x equals c, then f is continuous at x equals c. So if the function has a derivative, it is going to be continuous there. It does not work in the reverse. So you can't say a point is continuous, or rather, a point cannot be continuous and not differentiable. Okay, so if we take a derivative, it is continuous at that given point. All right, a couple examples here. Example 1, they want you to compare the left and right-hand derivatives to show that the function g of x, graph below, is not differentiable at the given points p. All right, so derivatives. As soon as I see the word derivative, I am thinking slope. And you won't have to plug into that huge formula we did in 3.1 because we were literally just finding the slope. So looking at point P, okay, from the left, okay, so I'm going to say g prime of x from left. If I go ahead and find the slope from the left-hand side as I approach it, it is going to be -1. Okay, so the slope's -1, that tells me my derivative, -1. From the right, if I was approaching from the right, that side is a +1. Since these two slopes don't match up, okay, so left we said -1, right is a +1. Since they are not the same, the function is not differentiable at point P. Looking at part B, you got g prime of x from left. So if I'm coming from the left, okay, towards P, we're using this line right here, slope would be 0. And then from the right, we would have a slope of 1. Again, since they don't match up, we would say that it is not differentiable at that given point. All right, last example we're looking at in the 3-2 notes. They give us a function. It's over the closed interval from -3 to 3. And they want to know at what points on -3 to 3 does the function appear to be differentiable. So I'm saying it's going to be differentiable for all x on the interval from -3 to 3, except, looking at this, we got a sharp change right there. So I'm going to say except at x equals -1. It's going to be a corner. And x equals 1. For x equals 1, there's two routes you could go here. We could say that it's a removable discontinuity. And actually, that's the route you have to go on that one, now that I think about it. You can't say it's a corner because it's actually not defined at x equals 1. So we're just going to go ahead and say it's a removable discontinuity. So it's differentiable for all x values on the open interval except at -1, +1. B, want to know continuous but not differentiable. It's going to be continuous, not differentiable at x equals -1. You look at it, limit from each side is good. Function is defined there as well, and it equals the limit, so it is totally continuous. And then for C, I want to know where is it both, neither continuous nor differentiable. That'd be x equals 1. So x equals 1, it wasn't continuous because it was a removable, and then it's absolutely not differentiable there either.